Welcome, everyone, to this episode of Manufacturing Talk Radio. I'm Tim Grady, and I'm here with my co-host, Lou Weiss, who's president of All Metals and Forge Group. You can find them at steelforge.com if you're looking for open die forgings and seamless rolled rings for industrial metalworking applications. Amazing stuff. I'm always surprised when I go in and look at this, the heavyweights, the large sizes that go into creating machinery or aircraft engines. Fascinating. Joining us today is Chris Nicholson. Chris is the founder and CEO of Pathmind. We're going to be talking about reinforcement learning. I don't know what it is, so Chris, educate us on what reinforcement learning is.
Yeah, sure, Tim. Thanks. So reinforcement learning is a kind of AI. So it's a kind of artificial intelligence. People talk about machine learning a lot, machines that learn. Those are algorithms. The way they learn is you expose them to data, right? You show them what's going on, and then you tell them what's right and what's wrong, right? So they'll slowly, they're like a little kid. I'm a father. We've all kind of seen toddlers grow up. They're like a little kid. They slowly learn what works, what doesn't, and they do it because you're exposing them to experiences, data of what happens in the world. So what reinforcement learning does out of all AI is it learns how to achieve goals, right? So you can go in and you can define the goal. Your goal might be, I want more throughput in my factory. I want fewer collisions, or maybe none, among, say, my AGVs or AMRs, right? So you can go in and you can define the goals, and the reinforcement learning through practicing in a simulation or practicing with little, say, robot arms somewhere in a safe room, it can learn how to do that, right? And then you can deploy it into operations. And when you deploy it, it often can really augment, it can really support your staff, right? And your workers in making sure that the flow keeps moving, right? That there's no starvation on any of the machines, right? That you can optimize for OEE, for example, by making smart decisions about how to schedule things to move through the factory more quickly.
So OEE, you just mentioned, define for it.
Oh yeah, overall equipment effectiveness, right? So it's just making sure it's avoiding time loss or downtime.
You know, it's amazing. I've been in manufacturing now just about 60 years, and I used to understand the language. And now we have to ask what OEE is. Is that like E-E-I-O, you know, the farmer's song?
Are you going to throw some alphabet soup at me, Lou?
So how does this work? How does this get implemented? How does the software become, do you do audits and analysis of a company's situation? You then make recommendations. I mean, I don't want to talk for you, but I'm not understanding. So
yeah, sure. So, you know, the factories we tend to work with have already started what they call a digital transformation. And what does that mean exactly? It means they started gathering data so they actually know and can point to the numbers that say what's happening in their factory, right? If you don't have the data, the algorithms can't do anything, right? So you have to take a step back and start there, gathering the data. But once you start that journey, once you start gathering the data and you wire it up and instrument it, right? You can start looking for patterns in the data, right? What action led to what result? And do you think that result was good or bad, right? So you can go into, say, a manufacturing execution system, MES, and you can suck some data out of it and start looking for patterns and figure out which actions were good and which were bad. And that's the nature of what reinforcement learning learns. Which actions are going to take you to the goals, the things you think are good. So that's what we would do is we would work with, or we and a partner, say another firm that works with manufacturing data, we'd go in, we bring the algorithms, they say, hey, I'll get the data for you, right? And we'll train our algorithms on the data. And the output of those algorithms will be suggestions. They'll be, we call it decision support, right? So people are making decisions at job shops and contract manufacturers every day about how to route items to different processing stations, which machine should process which order, right? You can get that very wrong, and that leads to a lot of unhappy customers, or you can get it very right and maximize your throughput, right? And so reinforcement learning can help you towards that goal, and it does so by working off the data that you give it.
So the reinforced learning, just to further qualify, has nothing to do with necessarily re-educating the employee. You're talking about re-educating the machines so that the employee has an easier time of doing their job.
A lot of the time, the employee will be teaching the machine. They'll be defining for the machine, here's what we want, right? So here are our goals. Here's what I look at in the, if they have the data, they'll say, here's what I look at in the data, right? So you can direct the attention of the algorithm. So the employee is in the position of the trainer, right? Not the trainee, in a sense. And the algorithm that you're getting and the algorithm is trying to learn from that. But what the algorithm can do is sometimes notice things, even after the employee trains it, it can notice things that might slip by, right? So we call that decision support. And what it means is the algorithm can come back to you and it can say, hey, I just noticed something in this order that's coming in, and you've got this one machine that's down and another machine that doesn't have the right operator on it. So I recommend machine number 3, right? So you can get some decision support there that might be counterintuitive, right? So in the end, the algorithm can actually start adding value. And what we see is these hybrids where human operators and the algorithms actually do a lot better together than either one would alone.
Got it. Got it.
Chris, one of the things we're seeing in production lines is machines placing parts on belts, parts being fabricated, they reach the end of the line, they're being looked at by machines to make sure that they meet the parameters of the part that was intended. Is that all part of this reinforcement learning? Is that what's happening with your software?
That can feed into it, Tim. So what it sounds like you're talking about is say flaw detection, right? Or kind of quality control, let's say, which is at the core of a lot of manufacturing processes, obviously. And you do that. Ensuring high quality is one goal you can define, and reinforcement learning can feed into that. You're going to need some other components to that system. For example, you need machines that can see or that can measure what's going on with the part, right? There's a lot of ways to measure things with those parts. One is what we call computer vision. That's just aim a camera at the thing. The camera is going to produce a stream of video or a JPEG file, a still image. And then the algorithm, the software inside the hardware, can look at that and it can pinpoint, oh, I see a flaw there. That weld didn't quite stick, right? For example, and it can automatically flag that and say that, you've got a flawed part here. Now, what reinforcement learning can do is one step beyond that. It can look at the process that led to the flaw, and it can say, not just, oh, you got a flawed part. It can say, we need to avoid these actions that lead to flawed parts.
It's fascinating. Manufacturing to me is fascinating. If you look at a potato chip, go to a Frito-Lay factory and look at a potato chip line where these, tens of thousands of potato chips are going past the employees who are plucking out the burned ones. And so that the best quality chip goes in the bag at the end of the line. I'm always fascinated about what's happening in manufacturing. So Can you give us some real world examples of where this is being used, what it's being used for, Chris?
Yeah, where it really excels. So you mentioned flaw detection. We actually see a slightly different use case really coming to the floor, and that's in machine and job scheduling, right? So machine and job scheduling is really at the core of efficiency and throughput. As we all know, and we hear about it every day, there's a severe labor shortage going on in America and many countries and companies around the world. And so people are looking for ways to keep their heads above water, to keep their throughput going, even in the face of constraints in various inputs, right? So there's a greater demand for automation. There's a lot of people interested in this. And with scheduling, what you get is these kind of complex systems, right? It goes beyond just saying, oh, there's a flaw in this part, which is, it's very valuable to say there's a flaw in this part, but that's something. But these systems, these larger systems, they're actually sometimes hard for a single person to understand in their entirety, right? Manufacturing processes are incredibly complex, right? And sometimes they move really fast. So one of the things that these algorithms can do that goes a little beyond what we can do as people is they can grasp complexity. They can understand if I do this down here, something else is going to happen on the other end of this complex process. And so a lot of scheduling tasks are like that, right? Things are moving fast, and inputs and the whole system is very sensitive to little changes at the start, right? So handling those scheduling tasks, and we can consistently show, say, more than 10% improvements in throughput by applying machine learning, which is huge when you think about it. People sometimes struggle for a 1% improvement in efficiency. We can get double-digit percentage improvements because the algorithms can actually understand more complexity than our human brains.
The employee, the trainer, who's training the software algorithms as to what they're supposed to be doing, does the human take a long time, or is it intuitive training? Will they understand it, or do they have to be deep trained in order to do the reinforced training, reinforced learning?
Yeah, that's a great question, Lou. So if a lot of the employees have deep domain expertise, right? They already put in the time to learn what they need to know, right? So what they need to do is show what they know to the machine in something it can understand. So that means kind of defining their goal. What's your KPI? How do you define throughput, right? Where are the places that you measure it? How do you make sure you're on track, right? A lot of people can actually really precisely say what they're following and what measurements they're tracking. And you can give those numbers to an algorithm. So that's not a long process, right? Mm-hmm. They already know it. If you have a programmer, right, or somebody who can do a little code, and there's a lot of those in the world, if you have a programmer, that person could phrase it in code, right, working with a domain expert, and express it to the algorithm. Now the algorithm, it trains itself, it learns on a chip, right? So algorithms process data on chips, right? And most of the chips, or a lot of the compute and a lot of the chips in the world is currently in the public cloud. So it's Amazon AWS or Microsoft Azure, right? These are data centers with huge amounts of servers, big stacks of chips, and on all those chips, you have data being processed, right? Meaning the data is being pushed through the algorithms, and as that data gets pushed through the algorithms, that's when the algorithms actually get trained, right? An algorithm's version of life is data getting pushed through it, right? So after you define the goal, you give it access to your data, you push the data through those algorithms, and then they start to figure out, oh, when I do this, then bad things happen. When I do this, then good things happen. And they do that on historical data, right? They're not screwing up your machines. They're practicing on data you've collected, right?
You had mentioned a moment ago about the person who does the coding. Mm-hmm. I'm not sure if a 20, 30, 40 man woman company has a coder. Mm-hmm. So is this program geared for perhaps larger companies?
It's a mix. So a lot of the people working with us will have some background in operations research, right? So some background in OR. I'd say mid to large manufacturers, mid-sized to large, are the ones who typically have put a little resources towards that. As soon as you have an analyst, or as soon as you have somebody with an OR background, you have someone who can work with these tools.
So I could teach my granddaughter how to do this.
Yeah, sure. It's what they call a Lowcode tool. So a Lowcode tool it takes snippets of code, but it doesn't require a lot of knowledge. It doesn't require a full software engineer to use it.
Okay.
Chris,
I'm happy to hear that.
Chris, one of the concerns that manufacturers have is in the areas of legacy knowledge and tribal knowledge. People my age retiring and not transferring the knowledge to the millennial that's coming in to run the machine and know that this particular machine has a hiccup every 30,000 cycles. Is this the kind of thing where reinforcement learning can help?
Oh yeah. Well, so it's the kind of thing that reinforcement learning could learn. It might have trouble if you asked it what it knew, it might have trouble coming back to you and saying, "Oh, that machine has a problem every 30,000 cycles." It doesn't necessarily know how to speak. It knows how to act, right?
Well,
But that problem you're talking about, Tim, that is profound and acute, right? We see that all over the place. There's a generational shift where a lot of the people who built these physical systems, they're phasing out. They're moving on to another stage of their life, and the people who are coming up behind and operating them may not have as deep of an understanding of how they work, right? And that's a huge problem because those systems need to be changed and they need to adapt, right? So we do need a deep understanding of them because when you're changing those one thing in a complex system, it affects everything else, right? So there's a really interesting field of study called naturalistic decision making. Naturalistic decision making is I lose laughing. It's actually
I can't even say it.
well, it's used a lot by the Army, by the armed services. They've run into the same problems. They'll get, you fight a war or two and you get a lot of really specialized knowledge about how things work. It's hard to pass on to the next generation, but you need to, right? Especially because you're operating complex machinery too, as a member of the armed services. So the Army really pioneered this. And they found ways of transferring knowledge from, say, an experienced veteran or sergeant to younger recruits. And now we're seeing that move into corporate America, right? We're seeing people, it's that tribal knowledge you're talking about. It's what we call tacit knowledge, right? It's not the book learning where you memorize a bunch of rules. It's really like, wow, I lived this for a couple decades. I know it viscerally, I know it instinctively what I ought to do, but I might find it hard to express. There are ways of actually getting that knowledge out of people that naturalistic decision-making researchers can do.
So when is the new software going to speak to make it even easier?
Well, oh yeah. So that's you're asking a lot of me here, Lou. You want to maximize throughput and speak? That that's a little more software development for me.
All right.
You mentioned low code software, and I'd like you to go into that. Lou and I have been working with programmers for years, and we refer to it as loco, as in crazy, because what they produce is sometimes not exactly what you expect them to produce. You're talking about pretty complex processes here, yet a fairly simple way to code to get to it. I'm fascinated. If you can explain that a little.
Yeah, well, the first thing I'll tell you about reinforcement learning is that what you do is you define your goals, but you don't necessarily tell it how to reach them, right? So defining goals is often easier than telling a machine every step it needs to take over many days or months to reach that goal. So the thing, reinforcement learning is powerful because it learns how to reach the goals you define. You don't, unlike other forms of industrial control where you give it precise instructions for every step, you don't have to do that with RL, with reinforcement learning. You define the goal, you let it loose on the compute in the cluster, and you say, figure out ways to reach that goal. And sometimes the ways it reaches that goal are quite counterintuitive. And that also is valuable because it can surface new strategies for you that you might not have thought of, right? So you're right, Lowcode, like machines do what you tell them, not necessarily what you want.
Right.
Right? That's the Lowcode part of any coding, low code or full code. The thing about reinforcement learning is it focuses on you defining what you want, and then the machine figures out how.
Does it look through things like supply chain data so that it knows, what's coming into my assembly line, I assemble, what's going out? Is that part of the matrix?
It can look at that. So the person working with it defines what the algorithm can see, right? So like a machine, unlike a human, a machine is not born with eyes and ears, right? So our eyes and ears are like our data ingest functions. We're all born with this stuff that lets us kind of relate to the world. A machine, an algorithm, is waiting for the user, say the employee or the programmer, to say, you should look at this. right? We define the eyes and ears of the algorithm. So if you've got data on what's coming in, or even in echelons upstream of you, here's what I expect from this distributor a few days out, you can say, I want you to keep an eye on those numbers. And when you define that, then it'll take that into account as it makes decisions. In fact, we're doing outside the walls, we're doing some pretty interesting work on what we call safety stocks. So you set the buffer stocks for multiple echelons along the whole supply chain, so that no matter what happens with supply and demand, and we've all seen a lot of supply and demand shocks, you've got enough to keep on meeting your SLAs and moving it downstream, right? So reinforcement learning has some pretty interesting applications in supply chain as well.
So your program, is this a program that's sold, leased? How does that work with regards to the client who's going to be using your program?
Yep. So our program is on the web. It's called web hosted. It just means we have an application, and you don't have to download it to your computer or your laptop. It's just in the cloud. You access it through a browser like Chrome or Internet Explorer or Firefox, right? Come use it, and so we're hosted there. We have free accounts so people can test it out, and there. So we're charging nothing for that experience of just seeing how it works. And then it's a monthly subscription. So in Silicon Valley, that's called software as a service, right? We just charge a monthly fee. If you're using it that month, you pay it, right? If you don't want to, you don't pay the subscription.
Okay, that being said, why don't you give us the URL where our listeners can come and learn more about who and what you're doing?
Yeah.
And how it would work for them.
Yeah, great. So I would recommend that they go to pathmind.com. That's P as in Peter, PATHMIND.com. And make sure that they look at our examples page. So we have a bunch of use cases where they can look at some of the scheduling applications that we've built, some of the supply chain applications as well as the kind of job and machine scheduling. And they can look at that and say, oh, that looks similar to what we deal with. And we're here, we have a team of software engineers who can help them adapt this software to their needs, right? So we're able to make adjustments for them to make sure it fits their goals.
Jim?
Fascinating. I'm sure that people who are in manufacturing have a better head for this to begin to understand it. I'm glad that you joined us to begin to explain it. A couple of things I'd like to share with you is that every month we put out a magazine called Manufacturing Outlook. Part of that is a technology outlook. And we'd love to have an article from you to give this some more form and information. If you are a writer, or you've got a writer who could generate one, love to have it.
Yeah, great.
Send it over.
Absolutely. Thanks for asking, Jim.
No,
we could actually call it Reinforcement Learning Outlook, because all the articles are an outlook.
Yeah.
Now, obviously, people will have to read the article to figure out what reinforced learning is all about.
Yeah.
But this is really terrific, and I think that we should probably have you on again when your software begins to speak.
Yeah, well, you should have my software on when it starts to speak. I'll skip it. You guys can talk to each other. How about that?
All right.
Well,
Deb.
Chris Nicholson of Pathmind, PATHMIND, pathmind.com. Thanks for joining us.
Great, Tim. Lou, thank you both.
Thank you.
And we appreciate all of you who are joining us. We are on video platforms like YouTube. We are also on C-Suite TV. We are on very many audio platforms. I think we're up to 30 or 40 audio platforms where you can hear the episodes. So come to us at jacketmediaco.com. Look at Lou's sitting right next to Lou on his right, that manufacturing talk radio icon. Those are all of our other shows. And thanks for joining us today on Manufacturing Talk Radio.